So today we're going to take a look at the 2024 Maths Advanced HSC paper, specifically part of section 2. We're going to go through questions 11 to questions 22. So question 11 says the graph of the function g of x is shown, and we have a graph below. Using the graph, complete the table with the words positive, 0, or negative as appropriate. So what they want us to calculate is the first derivative and the second derivative of g of x at x. Okay, so first and second derivative at each of these x points. So what you need to note is that the first derivative means the gradient, and the second derivative refers to concavity. Okay, so when we look at x equals -3, when x equals -3, that's this point here, and what we see is that the gradient is positive because we're increasing, and the concavity is negative, and that's because if you think about breaking this graph down into different parabolas, you could do something like that, and what you see is this is a concave down parabola. Okay, so something like that. Okay, so it's a concave down parabola, which means that the second derivative is negative, and as we mentioned before, the first derivative is positive. At x equals 1, what we see here, that's where x equals 1, we see that the gradient is actually 0 because we should be able to recognize that this is a horizontal point of inflection. And because it's a horizontal point of inflection, its concavity is also 0. It's neither concave up or concave down. As a matter of fact, it's an intersection between two concave up and two concave down parabolas, if you will. So the first derivative is 0, second derivative is also 0. Now what about x equals 5? At x equals 5, we have this point here. What we see is that the gradient, yet again, is positive, and the second derivative is positive because this is now part of a concave up parabola, which has positive concavity. So positive and positive. Question 12 says find the sum of the terms in the arithmetic series. Okay, so we know we need to find the sum, and we know that it's an arithmetic series. So we should know that the formula for the sum of n terms is n over 2 outside of a plus l, where a is your first term and l is your last term, and n is the number of terms. Okay, so as we can see through this series, we have the first term, which is 50. We have the last term, which is 2024. And what we don't exactly have is the number of terms, so n. So how we need to go about doing that is looking at the term formula where t of n is equal to a outside of, is equal to a plus n minus 1 times d. Okay? What we need to see is that, well, we want the total number of terms, which essentially means, well, what is n for the last term? Okay? So if the last term is 2024, we know that a is 50. We want to find n for the term that is 2024, because that will indicate what the number of items, or that will indicate the number of terms within this arithmetic series. And then we multiply that by d, which is the difference in the series, and we can see that it increases by 7. D equals 57 minus 50, which is equal to 7. You can also calculate this as 64 minus 57, which is also equal to 7, and that defines an arithmetic series. So our difference is 7. What we then have is 1974, if we just subtract the 50 on both sides, if we expand the bracket, we also get 7n minus 7. Then we're left with 7n equals 1974 plus 7, which is equal to 1981, and n equals 283. So we have 283 terms. So now when we take the sum of 283 terms, we have 283 over 2 outside of our first term, which was 50, plus our last term, which is 2024. If you plug that all in a calculator, what you end up getting is 293,471. That's it. Question 13 says the graph shows the populations of two different animals, W and K, in a conservation park over time. The y-axis is the size of the population and the x-axis is the number of years since 1985. Population W is modeled by the equation y equals a whatever, and population K is modeled by the equation. Cool. So they give us the graphs and then they ask complete the table using the information provided. Okay, so what we have is, these lines here, they give us the rough formulas, and we just need to figure out what the population in 1985 was, the percentage yearly change in the population, and the predicted population when x equals 50. Okay, so what we need to find is the population in 1985 for the K graph. So that's essentially what is B, and really all we need to identify is what is the y-intercept. Okay, so what we know is, that this line here is population W, and this line here is population K. That's really important to identify. The reason why we know which one's which is because W is increasing, is exponentially increasing, okay? And K is exponentially decreasing. How I know it's exponentially increasing and decreasing is the fact that this is greater than 1 and this is less than 1. You know, if we're multiplying by a factor greater than 1, we're constantly increasing, exponentially increasing. And if we're multiplying by a factor less than 1, we are exponentially decreasing. So when we need to find B, which is the essentially the y-intercept of the K graph, that is this point here. And if you just use a bit of inference, we can get this to be 280 because each little square is worth 10 population. And so if you count 1, 2, and then 3, you get an extra 30 on the 250. And so that's why B is equal to 280. Cool. The percentage yearly change in population. Now this requires you to have an understanding of exponential graphs. And so the percentage change is indicated by the factor that is raised to the power of x. So if we consider 1.055, if I take away the 1, I'm increasing myself by a factor of 0.055. And if I multiply that by 100, well, that's equal to 5.5%. If I look into the 0.97, which is the population K graph, take away 1 from that, that gets me minus 0.03. Multiply that by 100, multiply that by 100 and you get minus 3%. As you can probably infer that we are decreasing and the rate of decrease is 3%. So we fill in the blanks, 5.5% and minus 3%. The predicted population when x equals 50, they already give it to us for population K, but for population W, they don't. So what we need to do is go here, look at 50, and line it up to our graph. But what we then need to notice is that, well, the W graph doesn't extend all the way to x equals 50. So now what we need to do is just manually figure that out. And so because we know the equation of the line is represented by that first equation that I've circled there. We figured out, or actually they told us that a was equal to 34 times 1.055 all to the power of x. So that means when we want x to be 50, we just substitute 50 for x. And what we end up getting is 494.426. And so, yeah, when we want to predict the population, we just round down. And so it would be 494. Question 14. The curves y equals x minus 1 squared and y equals 5 minus x squared intersect at 2 points as shown in the diagram. Find the x coordinates of the points of intersection of the two curves. So to find the points of intersection, specifically only the x coordinates, we just need to equate these graphs, because when they equal each other, that just indicates that that's when they are going to intersect. So we have something like that. If we expand the perfect square bracket, we get this. If we collect like terms, we get 2x squared minus 2x minus 4 equals 0. You could factor out a 2. And then you can factorize. Okay. And this should be very simple to solve. All you need to understand is that you get x minus 2 equals 0, you get x plus 1 equals 0, and you get two solutions where x equals 2 and x equals negative 1. Now the next question says find the area enclosed by the two curves. So when we find the area between two curves, this is where we need to use integration. And because it is an area between two curves, we use a top minus bottom approach, because when we find the area at these points here, so we know this is minus 1, we know this is at 2. Essentially, in red now, if we do a top minus bottom, the top graph is this one here, which is 5 minus x squared. And we're finding this area highlighted in red there. And then when we subtract the other graph, the bottom graph, which I'm going to represent in blue, that's y equals x minus 1 squared. Well, we get the area below the curve between the x-axes, and that's there. And what we're left with is the shaded area that's in gray that they've kind of completed for you, but I'll just do it in green. So what we end up getting is we're left over with this area there. Okay. So we do top minus bottom, and it's going to be the integral between negative 1 and 2 of the top graph, which was 5 minus x squared, minus the bottom graph, which was x minus 1 squared. And this is with respect to x. We then need to do some expanding, where 5 minus x squared minus x squared minus 2x plus 1 dx. Do some more expanding. 5 minus x squared plus 2x minus 1. And collect like terms. So we get minus 2x squared minus 2x squared plus 2x plus 4. And then we integrate. So when we integrate, we get minus 2x cubed over 3 plus x squared, and that's because it becomes 2x squared over 2, and those 2's cancel out, plus 4x, and that's between minus 1 and 2. And then all we do is just kind of plug in our values, and so what we end up having is minus 2 minus 1 cubed over 3 plus, oops, sorry, that's my bad. So when we initially plug in the values for x, they should be at the top, which is 2. So 2, and then 2 squared plus 4 outside of 2, minus 2 minus 1 cubed over 3 plus minus 1 squared plus 4 minus 1. And I'm going to spare calculating all of that, but what you should end up with is 9 units squared, because this is an area that we're figuring out here. Question 15 says, initially there are 350 liters of water in a tank. Water starts flowing into the tank. The rate of increase of the volume of water in liters is given by that formula there, where T is the time in hours. And they say, find the volume of water in the tank when dV dt equals 0. Okay, so what we need, well, what they give us is dV dt, and we need V. Okay, and we need V when dV dt equals 0. So that's essentially the breakdown of the question. Now, what you should recognize is that you need to go from dV dt to get a formula for V, okay? And how you do that is through integration, okay? So if I integrate dV dt with respect to dt, that's going to be equal to the integral of 300 minus 7.5 t with respect to time, and that's indicated there. And if I integrate that, I get 300 t minus 7.5 t squared over 2 plus c, which is 300 t minus 3.75 t squared plus c. Now, to find this c, this constant, we need to look back into the question and see, well, do they give us sort of a point or a reference that satisfies the equation? And the very, very first sentence satisfies that. They say initially there are 350 liters, so that means volume was equal to 350, and initially means that was when t equals 0. So then we say that when t equals 0, V equals, what was it? 350. And so this becomes our equation for V, and then when we sub it in, we get 350 equals 300 times 0 minus 3.75, so 0 squared, plus C. We get 350 equals 0 minus 0 plus C, so 350 equals C. So therefore, the volume equation is given by 300t minus 3.75t squared plus our constant of 350. So then we know our volume, and now what we need is we need to answer the question, which is find the volume of water in the tank when dV dt equals 0. So now we need to know when dV dt equals 0. And that's going to be when 0 is equal to the equation of dV dt, which is 300 minus 7.5t. And so then we get 7.5t equals 300. And we end up getting that t is equal to 40 seconds. And so when we then need to figure out our volume, so we say when t equals 40, i.e. dV dt equals 0, volume is equal to 300 times 40 minus 3.75 40 squared plus 350. And what we end up getting is 6,350 liters. Question 16 says, flowers were planted in 2 gardens, Garden A and Garden B. On a particular day, 25 flowers were randomly selected from each garden and their heights measured in millimeters. The data are represented in the parallel box plots, and they give us those box plots there. Compare the two data sets by examining the skewness of the distributions and the measures of central, tendency, and spread. What you need to understand here is that this question is worth 3 marks, and we are doing a comparison of these two data sets, and we need to examine the skewness, the measures of central tendency, and the spread. Okay? So the fact that it's 3 marks and they want us to examine 3 different things means that we need to give 3 different answers related to each of the things that they want us to examine. So we need to give 1 examination on skewness, 1 on central tendency, and 1 on spread. Okay? So with skewness, what do we see? What we notice is that, well, we've got our medians here, okay, but represented by that line in the box plot there. And we see that garden A is negatively skewed, okay? And the reason for this is because, well, there is a significant tail of data that occurs well below the median, okay? So if you were to graph like a distribution of what this sort of thing would look like, it would look something like that, where you've got this tail here, and then that's something like the median. And garden B is positively skewed, where there is an array of data that is to the right of the median, okay, towards more positive areas. And so if we were to draw something like that, it would look something like this, where that's the median there, okay? And this is the tail, which indicates that we are positively skewed. So what we will say is that garden A is negatively skewed compared to garden B, which is positively skewed. Cool. Measures of central tendency is the next one. So let's just call that central tendency. Now, central tendency is the center, right? And what is the center of these graphs? Well, it's the median, okay? And we just need to compare these two. So if I just look at the median of garden A and garden B, I should see that the median of garden A is larger than that of garden B. So that's all we need to write. We need to say garden A has a higher median than garden B. Cool. The final thing is spread. Okay. So for spread, there's 2 things that you could answer on. The first is the more common, and that would be to do with the range. Okay. If you look clearly, garden A's range is much larger than, not much, but it is larger than garden B's. And that's because if you just take the largest value and subtract that from the smallest value, that ends up being bigger in garden A than garden B. The second thing you can pick up on is that the interquartile range of garden A is bigger than garden B. And the interquartile range is defined as Q3 minus Q1. So the upper quartile minus the lower quartile. And that's represented by the lines which sort of outline the box, okay? And what you can hopefully identify is that the distance between those 2 lines in garden A is larger than that in garden B. So what you can say is, you could say that garden, I'll just abbreviate here, garden A range is larger than garden B range, or you could say that garden A interquartile range is greater than garden B interquartile range. Either will suffice, but as long as you have 1 point for skewness, 1 point for central tendency, and 1 of those points for spread, you will get all 3 marks for this question. Question 17 says, in a particular electrical circuit, the voltage V across a capacitor is given by the equation here, where K is a positive constant and T is the number of seconds after the circuit is switched on. Draw a sketch of the graph Vt showing its behavior as T increases. So this is an exponential graph, and what you need to know or notice is that it is limiting to a certain point. And where that limiting function comes from is from the E, okay, where it's an exponential. So what we can say is that as T approaches infinity, this e to the minus kt, which is essentially e to the minus infinity, well, it approaches 0, okay? And the reason why we know it's 0 is because, well, if you think about a really, really large negative number and putting that to the power of something, it's going to tend towards 0. And if you just experiment, if you have a calculator on hand and you type e to the power of minus 99999, what you'll get is a number that is either 0 or really, really close to 0, okay? And that sort of explains that relationship there. And so now let's imagine that this whole section here was just 0. So that means this becomes 6.5 outside of 1 minus 0, which is just equal to 6.5, okay? So that means as t approaches infinity, this whole graph V, this whole graph V of t approaches 6.5. Okay, so as t gets really, really, really large, the graph, the y value of the graph is approaching 6.5. So if we draw the sketch, we need to make sure we label our axes. So that's V and that's t. And we know that we start at 0 because if t equals 0, if you plug in t equals 0 here, you're going to get v equals 0. So we start at 0. And we know that this is going to approach 6.5. So let's draw like a dotted line here. And as you can see, this is what the graph would look like, where it approaches that line at 6.5. Question B says, when t equals 1, the voltage across the capacitor is 2.6 volts. Find the value of K, correct to 3 decimal places. So the information says at t equals 1, V equals 2.6. And so we just plug in those numbers into the equation. So we get 2.6 is equal to 6.5, 1 minus e to the minus k times 1, which if we work this out, so it's equal to 2.6 over 6.5, and that's equal to 1 minus e to the minus k. Why is it just e to the minus k? Well, if you take minus k and multiply that by 1, then you just get negative k. And so then you get 1 minus e to the minus k is equal to 2.6 over 6.5, which works out to be 0.4. Rearrange a little bit, you get e to the minus k equals 0.6. And now to figure out k, you got to log both sides. So log of e to the minus k is equal to log of 0.6. Go up here. Log of e to the minus k is just minus k. And log of 0.6 stays as log of 0.6. And then so that means k equals minus log of 0.6, which is equal to 0.51082, and to 3 decimal places is equal to 0.511, because we round up from that 8, and let's just specify that it's 3 decimal places. Cool. So we know the value of k now, And the final question says, find the rate at which the voltage is increasing when t equals 2, correct to 3 decimal places. So we want the rate, okay? And the rate is dv dt, which that means we need to differentiate this graph, okay? Before I differentiate, I'm just going to expand v. So we know v equals 6.5 outside of 1 minus e to the minus kt. So if we expand that, it's equal to 6.5, minus 6.5 e to the minus kt. We know what k is, I'm just going to keep it as k for now. And if we differentiate that, we get 6.5k e minus kt. And that's because the minus k goes to the front of this minus 6.5. Those negatives cancel each other out, and we're left with just 6.5k. And then the e stays the same. And we need to just work out when t equals 2. So at t equals 2, dv on dt is equal to 6.5 times k times e to the minus k times 2. And if you just plug all of that in a calculator, noting that k was equal to 0.511, then what you get is that it was equal to 1.195, and that's the 3 decimal places. And units is really important here. So this is volts, v is volts, and t, as we noted, was the number of seconds. So dv dt is volts per second. Cool. Question 18 says, in a game, the probability that a particular player scores a goal at each attempt is 0.15. What is the probability that this player does not score a goal in the first 2 attempts? So for them to not score a goal, so the probability to not score is equal to 1 minus the probability of them scoring. And so that's equal to 1 minus 0.15, which is equal to 0.85. And so that means the probability that they don't score twice is equal to 0.85 times 0.85, because those outcomes need to happen twice, and that equals 0.7225. B says, determine the least number of attempts that this player must make so that the probability of scoring at least one goal is greater than 0.8. So what we need to know is this whole idea of scoring at least one goal is a really important principle within probability. And so generally the probability of at least one is 1 minus the probability of none happening, okay? So what we need to figure out is the number of attempts where the probability of scoring at least one goal, or 1 minus the probability of none, is greater than 0.8. Okay, so how many attempts would it take for that to actually happen? And so for a player to not score any of their n attempts, that's essentially equal to the probability. So this probability of none is essentially equal to the probability, is equal to the probability that the player misses n shots, which is equal to 0.85, because that's the probability that the player misses a shot, to the power of n. So what we need to figure out is when 1 minus 0.85 to the power of n, which is the probability that at least one shot is made in n attempts, when that is greater than 0.8. Okay, what we get is that it's when 0.85 n is less than 0.2. If we take the log of both sides, we get this. Then we can take n ln 0.85 is less than ln of 0.2. And then we divide by log 0.85 to just isolate the n. And what you need to note here is that log of 0.85, because 0.85 is less than 1, this number is actually negative. And so when it's negative, instead of this being a less than, it becomes a greater than, because when we divide or multiply by a negative and it occurs over a greater than or a less than sign, we flip the direction of the sign. And what we get is that 0.2 over ln 0.85. And then if we plug that into the calculator, it's equal to 9.9, which then means we need 10 attempts. The reason why 10 attempts is because that's the first whole number greater than 9.9. Okay, if we take only 9 attempts, then the probability will be less than 0.8. And if we take 10 attempts, the probability will be more than 0.8, but that's all we care about, right? That's the minimum number of attempts that it will take us to have a probability greater than 0.8 there. Question 19 says, sketch the curve y equals x to the 4 minus 2x cubed plus 2 by first finding all stationary points, checking their nature, and finding the points of inflection. So what I like to do is, before anything, I like to figure out the first and second derivative. So the first derivative is 4x cubed minus 6x squared. And the second derivative, y double dash, is equal to 12x cubed minus 12x. So stationary points, stat points, are at y dash is equal to 0. And so that's when 4x cubed minus 6x squared is equal to 0. You can take out a factor of 2x squared, and you're left with 2x minus 3. And then you have stationary points, or x coordinates at x equals 0 and x equals 3 on 2. So what you then need to do is focus on each of those points, okay? So let's focus on x equal to 0. So at x equals 0, we need to know that y is equal to 0 to the 4 minus 2, 0, 3 plus 2, which is equal to 2. Therefore, we have a point at 0, 2. So this is a stationary point, but we need to know the concavity. And so that's going to be through y double dash, which is equal to 12 outside of 0 squared minus 12 outside of 0. And that's just plugging it into the formula, which is 0. So therefore, we have a possible point of inflection at 0, 2. Now, it's a possible point of inflection. We need to check if it is. And how we do that is checking that there is a concavity change. So if I have just a little table here for x and y, and I just include 3 values for x that I'm going to test. So at x equals 0, we know the concavity is 0. And then we test a point which is slightly above 0, which is 0.1, and slightly below 0, which is negative 0.1. If we plug them into our y double dash formula, what we get is that when we plug in x equals 0.1 into that y double dash formula, we get a negative number. And if we plug in the minus number here, we get a positive number. And because there's this change in concavity, so concavity change, therefore we have a point of inflection at 0, 2. However, it's also a stationary point, which means we have a horizontal point of inflection at 0, 2. Cool. Now, once that's done, we then test the next stationary point. So at x equals 3 on 2, we know that y is equal to Yep. So we know that y is equal to 3 on 2 to the power of 4 minus 2 outside of 3 on 2 to the power of 3 plus 2. If you plug all that in the calculator, you end up getting y is equal to 5 on 16. And if you figure out y double dash, that's equal to 12 outside of 3 on 2 squared minus 12 outside of 3 on 2. And you don't really need to calculate this. All you care about is the sign, and it's greater than 0. The fact that it's greater than 0, therefore it means you have a minimum because it's concave up. So minimum at 3 on 2, 5 on 16. So that's great. We've got our stationary points sorted. Now we need to sort out if we have any points of inflection. And so possible points of inflection are at y double dash equal to 0. And so that's when 12x squared minus 12x is equal to 0. So that's when 12, if I just take it a 12x, I get this. And so x equals, x equals 0 or x equals 1. We already tested a point of inflection at x equals 0. Okay, so that's all done because that was tested over here. So now we just need to test x equals 1. So at x equals 1, we know that y is equal to 1 to the 4 minus 2, 1 cubed plus 2, which is equal to 1. So therefore we have a point 1, 1, but we just now need to test that it's a point of inflection. And so if I just do a test for a concavity change, we have x equals 1, and we know that y double dash is equal to 0. So test the point that's slightly larger and slightly smaller than 1. And what we see is that this is positive, this is negative, and then so concavity change, therefore point of inflection at the point 1, 1. So now we've got everything that we need to draw our graph. Okay, so when I draw the graph, I'm just going to draw it as best I can. I'm going to draw it here. So what I like to do first is just map out what my stationary points are, particularly like my minimums and maximums. So here we've got the minimum at 3, 2, 5, 16. So let's just say 3, 2 is here. Okay, and it's a minimum, so let's just call it there, and that means this is 5, 16, and you can label it here, so 3 over 2, 5 over 16. Okay, you know that this is a minimum, so we're going to be slightly increasing at this point. We know that there is a horizontal point of inflection at 0, 2, so let's call that there. Okay. And they're all the stationary points that we have. So a horizontal point of inflection is going to look like that. The fact that this is a minimum, it's just going to keep rising like that. And what we also need to, so I'm just going to label 0, 2 there. And then what we also need to label is our point of inflection, our regular point of inflection, which is right here. And that is 1, 1. Okay, so I can put a 1 there, 1 there. Good practice is labeling your axes, so y-axis and x-axis, and that's it. That is our graph. Question 20. A vertical tower, TC, is 40 meters high. The point A is due east of the base of the tower C. The angle of elevation to the top T of the tower from A is 35 degrees. A second point B is on a different bearing from the tower as shown. The angle of elevation to the top of the tower from B is 30 degrees. The points A and B are 100 meters apart. Okay, so they give us all that information. Really, there's no information to add because it's just all given here in our graph. Show that the distance AC is 57.13 meters correct to 2 decimal places. So AC is this line here. And what we should recognize is that, well, AC is part of a right angled triangle. Okay, if I draw it here, we've got a right angled triangle where that's A, C, and the top of the tower was T. This is 35 degrees. This is 40. So just using basic trigonometry, we see that AC is the adjacent side and TC, which is the 40 that they give us, is the opposite side. So opposite over adjacent is a formula that we should know and be aware of, and that relates to tan. So tan 35 is equal to our opposite side 40 over our adjacent side AC. So AC is equal to 40 over tan 35 degrees, and that's equal to 57.13 if you just plug it into the calculator and round that to 2 decimal places. B says find the bearing of B from C to the nearest degree. Okay, so this one's a little bit more involved. So we know this is now equal to 57.13. And they want the bearing of B from C. Okay, so from C. So imagine C is 90, like this line that I've drawn here is like a north line, and A is something like a east line, right? So the bearing is read from north all the way around clockwise until we get to B. So what it's going to be is 90 degrees, right? This angle here to go from like north to east, plus this angle here, okay? Which is the angle in this triangle, okay? Or just angle BCA. Okay, so we need to find angle BCA. Okay. Now let's have a think here. In order to find that angle, we can use the cosine rule. And to use the cosine rule, it requires us to have this length here, which we have. We have 57.13 as well as 100. But it also requires us to know this length here, which we don't currently know. But using a very similar principle to what we did to find AC, we can do the same thing to find BC, and then we can use cosine rule to find the angle. Okay, so to find BC, what we're going to do is we're going to use SOHCAHTOA. I'm going to skip the mapping out of it because it's very similar to part A. But that's what we get. We get BC equals 40 on tan 30. And so BC equals 69.28. Okay. Now, we want the cosine rule. And we're going to use the cosine rule for the angle. So cos of the angle BCA. Okay. Now, this is equal to your adjacent sides squared and added to each other, minus your opposite side, right? Or the side like that's relative to the angle, that matches to the angle, all over two times your adjacent sides multiplied together. So let me actually just write the formula down here. So it's cos of angle C is equal to A squared plus B squared minus C squared, where minus C squared is the side that corresponds to the angle C, all over 2 times A times B. Okay, and if we just, plug in our values, we get 57.13 squared. This is going to intervene here. So we get 57.13 squared plus 69.28 squared minus 100 squared. Okay, so A squared plus B squared minus C squared, all over 2AB, which is 2 times 57.13 times 69.28, which is equal to minus 0.2446 and so on. And then we cosine, so angle BCA, which is equal to the inverse cosine of that. which is equal to 104 degrees. So now we found that this angle here is equal to 104 degrees, but our bearing is equal to 104 plus that 90 degrees that we established earlier. So bearing of B from C is equal to 104 degrees plus 90 degrees, which is equal to 194 degrees. Question 21 says, a researcher is studying anacondas, which is a type of snake. Dataset recording the age in years and length in centimeters of female and male anacondas is displayed on the graph. Anacondas reach maturity at about 4 years of age. So they give us all this great information, and they give us a graph here showing how anacondas increase in their length as they increase their age. And we have a key here. The white squares represent female and the black circles represent male. The question asks, write 3 observations about anacondas that may be made from the scatter plot. Note that no calculations are required. So these are purely just observations that we need to make based off the scatter plot. So just focusing in here, what do we notice? Well, we should notice that one really easy observation to make is that the length of snakes increase as they get older, okay? That's a very easy observation. And even after they hit maturity, which the question specified was at 4 years, they still grow. They still get longer, okay? So one observation that we can write there is anacondas grow as they get older, even after maturity. The more details, the better, because, just more opportunity to win more marks there. So I wouldn't just say anacondas grow as they get older. Adding that extra layer of detail where even after maturity is really, really important, because it conveys to the marker that you kind of really are understanding the data and making some solid observations. What's another observation we can make? Well, what we can notice is that consistently, the length of females is larger than that of males, okay? So that's another observation that we can make. Females are longer than males. And you can add an extra layer of detail by saying at all ages. And a third observation that we can make maybe could be a little bit more involved to recognize, but it's to do with the rate and the rate of increase. So if you look at how fast females are growing, they're growing faster than males. So you can see that they start, at a very, very close point together. Females are still larger than males, but they start quite close. And what we can see is that, they get quite far apart, which would indicate that females grow faster than males, okay? So that's our third observation. Females grow faster than males. That's it. There are 3 observations. Question 22 says the graph of the function f of x equals the natural log of 1 plus x squared is shown. And then they give us a graph. Prove that f of x is concave up for this range here, okay? So to prove that a graph is concave up or concave down, we need to look at the concavity, okay? And to look at the concavity, we need to derive, okay? So let's derive the graph. So we have f of x equals the natural log of 1 plus x squared. We should know our derivative rules. So if we derive this, we get 2x over 1 plus x squared. Now we need to use VUV to figure out the second derivative. So if we were to imagine that the graph, the top is represented by u, the bottom is represented by v, we have u equals 2x, u dash is equal to 2, we have v is equal to 1 plus x squared, and then v is equal to 2x. We know that the derivative is equal, so like f double dash x would be equal to the VUV rule, which is v u dash minus u v dash over v squared. And so that's just equal to, if we just kind of follow our VUV rule, v u dash is 2x, it's v dash. So v u dash would be 2 outside of 1 plus x squared minus 2x times 2x all over v squared, which is 1 plus x squared, all squared. Okay, so if we were to just simplify this, I'm going to spare on the calculations. We get 2 minus 2x squared over 1 plus x squared, all squared. Okay. So what we need to know is that, or what we need to understand is that this graph, f of x, is concave up when this is greater than 0. Okay? When that's greater than 0, when the concavity is positive, that means we're concave up. What we should note is that the denominator is always positive. Denominator is always positive. So for every x, it's always going to be positive. And the reason why is because all of that is getting squared. So whether our term here is positive or negative, that's going to be decided by our graph, our numerator. Okay, so therefore, concave up when 2 minus 2x squared is greater than 0. Okay, if we factor out the 2, we get 2 outside of 1 minus x squared is greater than 0. And this is a difference of 2 squares. So what we now do is we can draw a graph and identify when this graph is greater than 0. So we should know that this is a graph that is concave down. Reason why is because the x squared is negative. So it's a concave down graph. And our x-intercepts are at 1 and negative 1. And we should know that because if we were to solve for this equation here and let that equal to 0, that's what we'd get. And when we look at when the graph is greater than 0, we see that that is this whole period, this whole range here. And that's characterized when x is between -1 and +1. Therefore, when -1 is between x, which is between +1, which is exactly what they were asking for in the question. Cool. Okay, so question 22b says a table of function values correct to 4 decimal places for some x values is provided. Using the function values provided in the trapezoidal rule, estimate the shaded area in the diagram. Okay, what you need to notice is that it only gives us x values between 0 and 1. And the shaded area is between 0 and 1, but also between -1 and 0. But what we then need to recognize is that the shaded area on the right-hand side is exactly equal to the shaded area on the left. So if we just were to multiply this area by 2, we would be able to estimate our area there. Okay? So now we just need to apply the trapezoidal rule. So area is equal to, so 2, which is 2 times. So that's because we are trying to figure out, it's because we need to double each half. Okay, so we're only calculating one of the halves here, and by multiplying it by 2, we're going to get the second. It's going to equal to, so then you have a numerator, which is equal to 1 minus 0, which is the difference between your first and last x value, over 2, times the change in x. So each x point should be uniform, okay? And as you can see here, we are increasing by a factor of 0.25, and that's all multiplied by the y value of the first and the last term, okay, added together, which is 0 plus 0.6931 plus 2 times the rest of the terms, okay, which is 0.0606 plus 0.2231 plus 0.4463. Okay, and so we've applied the trapezoidal rule there. If we work all of this out, we eventually just get 0.53827, which is equal to 0.54 units squared, and that's the 2 decimal places. I know it doesn't specify that we need to round it to any sort of placing, but 2 decimal places is quite standard. And yeah. So part C says, is the answer to part B an overestimate or underestimate? Give a reason for your answer. So essentially this is just saying, is our estimate in part B, so the area that we calculated using the trapezoidal rule, is it an over or an underestimate to the true area of the diagram? Okay. So the true area is the shaded region. And what we've done is, well, if you consider we have 0.25 here and 0.75, and we create trapezoids, okay? So dot, 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 and there, and then we connect it all together. You can probably already see by the way that I'm constructing these lines, but we are overestimating, okay? And the reason why is, well, we should know that when our graph is concave up, we overestimate, and when it's concave down, we underestimate. So down below, I'm actually just going to exaggerate what that sort of looks like, but your answer would essentially say, from part A, we know that the graph is concave up between -1 to +1. Therefore, excuse me, therefore, we will be like part B overestimates the true area of the graph. So that's what the answer would be in written form, but I'm just going to show you what I mean when we overestimate and underestimate. So let's assume we have a graph, and this is concave up. Something like that is concave up. And let's say we draw our line segments here. And essentially we're just connecting the dots and using trapeziums in this sort of exaggerated way. What you can really see, oops, that's like very wonky. What you can see is like we have these little sections, which I'm going to do in green, like these little sections here, which we are overestimating. And that's what happens when it's concave up. In another instance, when it's concave down, so I'm just going to rub all this out. When it's concave down, So something like that. And we do our line segments. What we see is that when we connect the lines, it actually comes under the curve. And so we underestimate by like these green amounts now instead of overestimating. And this happens when we are concave down. Okay, so when our concavity is negative and we're concave down, that's when this occurs.